Welcome everyone. This is Physics Prism. Again up with Wave Dynamics Part 2 of our previous lecture. In our previous video, we left off on this portion. We have just applied the Fourier transform, and we have got the general SHM motion, and we got Y tilted. Now, in this video, we are going to explore how we get exactly the wave function that defines the motion. Okay, so what to wait for? Let's get started. Now, if we take our previous y tilted that we got in our previous page, here if we take this previous y tilted and apply inverse Fourier transform, then we would get our y in natural space, right? So let's do that. Let's apply Fourier inverse. So we get y as a function of t to be the integral from negative infinity to infinity y tilted. So y tilted is nothing but that's a e to the I omega t plus qx, right? And the right moving wave, that is b e to the power one thing I have done little mistake. Here minus qx. So you can understand by looking at the equations that what kind of equations these are. These are nothing but waves. This is a left moving wave, and this one is a right moving wave. But hold on, do we actually require the left moving wave? In our previous video, we have told that at I'm extremely sorry for this inconvenience, but in our previous lecture we have told that at x equals to 0, our y, the displacement, is fixed, that is if we look at the wave, it's actually moving this side and it's never coming back because it's never bouncing. If it were also fixed over here, then the wave would have bounced and interfered and there would have been a much more interesting things, but that is not going to happen. So we can say that our amplitude of the left moving wave is 0. Fine then. So what next? See, if that becomes 0, then we have y as a function of x and t is nothing but the integral of a being 0, so b iota omega t minus qx d omega by 2 pi. Okay, d omega by 2 pi. Fine. Now what next? See, if we look at this thing very close, we can see that if we put x equals to 0 and apply the boundary conditions, then we get something like this. This is the integral from negative infinity to infinity b e to the power omega t d omega by 2 pi. But wait, this is exactly equals to f of t. We have defined it earlier. Where have we defined? Here. Here we have defined at x equals to 0 and at any time period timestamp t, we have the displacement in y as f of t. Right. This is the oscillatory function actually, we can say. So we get to know that b is nothing, right? But it is nothing, but it is actually f tilted of omega. If you do some Fourier analysis, you can get this. This is actually the Fourier coefficients, right? It's obvious. Now look, this is what we got. But suppose there is some damping. So in case of damping, the situation changes, right? So let's consider some damping because we are dealing with real world entities. So let's say in case of damping, not damping, damping. So in case of damping, what happens? If we take our real function, so we can genuinely call this, if it is a case of damping, then there will be some function, right, that we got, not some function actually, the thing that we got, b, our amplitude, and we take omega out, so t minus q over omega x d omega by 2 pi, right? So this is, now how to solve this? Well, this is very easy to solve. You know what is omega, sorry, what is q? Q is nothing but it's omega squared minus iota gamma omega over c square and the root of that, right? So this is nothing but omega over c into 1 minus iota gamma over omega to the power 1 by 2 or root, right? So put that over there. Put that over there. What do you get? Let's put it over there. Let's put it over here. Just there. Okay. So what we get? You can see this term at the top, at the exponent, will be e to the I omega times t minus x over c plus I iota gamma over 2 omega c x, right? D omega over d pi, 2 pi, sorry. Now look at it very closely. Do you find something that cancels? Well, yes, why not? Uh, which cancels? I don't know. But wait, how do we get here? Now you must be wondering that what are you doing? We didn't arrive at Q at like this, right? Well, yes, we have just have a little assumption that gamma is much less than omega. If we assume that, then for all frequencies present in this function, then for all the frequencies in this function, our q will be omega over c times 1 minus iota gamma over 2 omega. Now I hope you can understand what we have done, right? Well, that's nice. So, what next? What next? Well, what next? This is very easy. We have almost got what we wanted. So we can say that y is nothing but e to the gamma x over 2c times the integral from minus infinity to infinity f tilted of omega times e to the iota t minus x over c d omega by 2 pi. This is not too tilted but 2 pi. Yeah. So that's it. This is what we wanted. And if we do this is actually in form of Fourier inverse. So we get x as a function of y as a function of x and t to be e to the power minus omega x over 2c times f of t minus gamma over c, not gamma, x over c. Isn't it? Isn't it? Yes, this is what we have arrived at. Now, how does it look? Well, that is pretty much as we have done in our damping. In our class 11th and all that, we have learned how damping look like. So this is the function like this. To draw it better, let's draw it better, and now it will be much better. Well, so what is this? This is actually a straight line. It will be converging like that and converging like that. The amplitude would follow this kind of behavior. Okay, let's move it a bit up like that, and this one. Well, so let me try it again once more. As you can see, the amplitudes will just touch like this and it will converge. You can understand, I hope so. This is not required also. We can make sense that this is the thing what is happening, right? Now, since we have completed our courses of what is the wave function and all that, we have learned it. Now we may move on to some very interesting phenomena that actually happen in our day-to-day life. And one of the most interesting phenomena out of this is nothing but forced oscillations. So we will be just starting out what are forced oscillations and telling about the Lagrangian all that. But today we won't be able to finish forced oscillation. Today we are just starting it up, and in our next session we will complete forced oscillation, damped oscillations, and all other interesting phenomena like resonance. Then we have oscillations with damping and external forces, all that. But today let's start off with forced oscillation. Just the introduction, what is a forced oscillation? So these are actually one dimensional systems that we are going to consider. We are going to consider only the one dimensional systems. Okay, now the Lagrangian equation is this. I hope you know this, and the derivation of this equation deserves a separate video. Okay, and Lagrangian for a forced oscillation is nothing but something like this. Oscillator Lagrangian looks like this. Okay guys, now here we define something, that F is a generalized force. What is the meaning of a generalized force? Does that have any significance? Yes, it does have any significance. A generalized force is a kind of force that is applied all throughout the string. Well then, how does it look like? This is a periodic force. It is of form like this. Now how do we arrive at this? Well, that we will cover in our next session or on a separate video. Well, now what? Now what we do? See, we know if we have this kind of equation, differential equation obviously, then our general solution is nothing but q equals to a cos omega t plus some phase difference phi, right? But if we add up an inhomogeneous part, here what is happening, when we are adding this force to it, we are actually not getting this differential equation to be 0, but we are getting it to be f cos gamma t plus beta. Okay, so this is a non-homogeneous equation. Fine. So what to do? How to deal with non-homogeneous equations? Well, to tell about that, let's add a page first. Here you go. Let's talk about this non-homogeneous equation and how to solve this in here. See, we have our thing, something like this, something q double dot, or wait, we have that equation, and this equation has a solution something like this. There will be the homogeneous part of the equation plus phi plus some additive part, that is also a function, that is also a function of time. And if we have our function of time to be b cos gamma t plus beta, then putting in the equation of motion, we get that b must be f over f into this thing, not r gamma. Okay, we will get this. How? We will put it into the equation of motion. Where? Which is the equation of motion? The Lagrangian. Okay, so this is your homework, to put it over there and check what b is coming up. This is your homework. I'm just getting it over here. Homework. derive B from the total derivative of the partial derivative minus the partial derivative is equals to 0. Okay, do it at your home. This is a very interesting thing and I hope we will get some interest. So the B will come up this. This is what you will get, and you must get this. If you are not getting this, then there is something really wrong with what you have got. Okay, so what finally do we observe? What finally do we get? We get nothing but then q as a function of t will be a cos omega t plus phi plus f into this times cos gamma t plus beta. Here omega is not equals to gamma. Only when omega is not equals to gamma, this is possible. But if omega is equals to gamma, then we get something very interesting that is known as resonance. And today we won't cover the resonance, but today we end up over here. Continuing on our next lecture, we will be talking about resonance and all that. And I will be linking the link of this PDF in the video description. Go through that. If you have any problem, feel free to comment. And if you have liked this video, like, comment and subscribe. Signing off, Physics Prism.